connecting? How do I know if it's recording? Oh, okay. Right. So yesterday we looked at the reaction of amides. Okay, so amides can be reduced to amines. Its respective amines depending on which amides you started with. And then we've also looked at the hydrolysis of amides, where the amides bond are being broken using acid or using base catalyst. So next we are going to take a break from this amide bond because later on we will revisit it, but in terms of peptide bonds, okay? So first we are going to look at amino acids. Most of you are familiar with this term. I'm sure you are more pro in this area of chemistry, right? Amino acids, that's the next learning objective that you will look at. Before we look at the first learning objective, let's just introduce or just recall back what amino acid is. So amino acids contain the basic amino group. So what I mean by basic there is alkali, okay? So the NH2 group in the amino acid is coming from the amine. And the acidic group is the COOH group. So the general structure for an amino acid is that you have a carbon center. It is attached to amine group, whichever position you want to put the amine, acid group, COOH, and there's a hydrogen there. It usually has this hydrogen. And you can see here there's an R group. So that R group, what do you call that R group? Just R group. Or side chain, side group in bio? What do you call that? You know, all that's different parts of the amino acids, right? That makes it an alanine. I don't know. That's the only thing that I could remember on top of my head, okay? So this R group, it depends on what group is attached to this part of the molecule that differentiates one amino acid with another. Okay, so thankfully, the R groups, somehow it's no longer mentioned in your syllabus. So I don't know if you, well, you are not supposed to memorize them. In chemistry, you definitely don't have to memorize them. So I assume that if they want to ask you an amino acid questions in the exam, they will give you the structure already, okay? Or they will give you a list of R groups. Okay, so the general structural formula for an amino acid is RCH. So that C is your central C. And then you've got a hydrogen, you've got an amine group, and an acid group. Okay. Should they go in that arrangement? Well, not necessarily. You can always write RCH, COOH, followed by NH2. Okay. Right, first example, the simplest amino acid is glycine. The biological name is glycine, but in chemistry we call it an amino ethanoic acid. So let's start drawing. If I would just like to draw out the displayed structure so you can see all the bonds. So for an amino acid, you have a central carbon with an amino group, NH2. You also have an acid group, COOH. You've got a hydrogen, and your R group is now also a hydrogen. Okay, so that's the simplest R group you can find, and this is called a glycine, but we call it amino ethanoic acid. Why? If we count the number of carbon, there's 1 carbon, 2 carbon. So the name amino comes from the amine group. And then the ethanoic acid comes from the 2 carbon atoms. and the oic acid is just the COOH, okay? Of course, if your R group is something else, then the name changes. All amino acids will have, except this one, except when you have glycine as the R group, the central carbon will be a chiral center. Okay, I don't know if I have a list of R group here. Where can I find that? Amino acids. Because in the new syllabus, definitely it's not in there. Here. Okay, so this is the older syllabus, and they give you a list of R groups in the data booklet. Okay, the data booklet was provided in the exam, but for you, no, it's no longer given. Okay, so they will tell you when your R group is CH3, then it is an alanine. When your R group is CH2COOH, then it's aspartic acid. So the R group is located here. Okay, so you just change that R to any one of these given groups in the list. Okay. Right, we go back here. So that means if your R group is other than hydrogen, that makes your carbon center a chiral center. In this case, this is not a chiral center, okay? So if there is a chiral center in the molecule, then of course you will have this isomerism called the optical isomers, and you should be able to draw the optical isomers as a mirror image to each other, okay? And when drawing mirror image of each other, you should draw your bonds in 3D drawing, okay? Can you just draw one of the dotted bonds as a solid line, because that's how we learned it. In a tetrahedral structure, we usually have two solid lines, one wedge bond, one dotted line, where the wedge bond is coming out of the paper, or we say in front, and the dotted bond is to the back. Maybe I will say to the front. Okay, so wedge bond will point out of the paper, and dotted bond will go back to the back of the paper. Okay, so I will not go through drawing this. We've already done a lot of practice on this. Now, the first learning objective, I think this is the only learning objective for amino acid, is to describe the acid-base properties of amino acids and the formation of Zwitterions. Have you heard of the term Zwitterions before? Oh, so you don't learn Zwitterions. To include the isoelectric point. What about isoelectric point in bio? Have you heard of that? No, okay. So two new terms that we are going to look at for amino acids. Okay, so amino acids can undergo internal acid-base reactions. So that means in that one molecule of amino acid, there's the acidic part and there's the basic part. So what can happen is the acid and the base can react internally. Okay, so that means it reacts within that one molecule of amino acids. That's what it means by internal, okay? To form a dipolar ion known as Zwitterion. So I'll show you what a Zwitterion is. This means an internal transfer of a hydrogen ion from the COOH group. That's the acid. Acids are proton donor or H plus donor. To the NH2 group, bases are proton acceptor or H plus acceptor to leave an ion with a positive and negative charge. Okay, so what do we mean by this? So let's start with a neutral amino acid. So I will just draw my hydrogen and R top and bottom, just get it out of the way, okay? I'll have my COOH here, and then my NH2. Actually, I would want to color code them so you can see what's happening. The acid group, I will change color. Okay, red is fine. Maybe blue. And then the amine group, I change color as green. Okay, so just remember that the acid is proton donor. It wants to give away its proton. Okay, and an amine, which is a base, is proton acceptor. Okay, so in aqueous solution, or if we just leave the amino acids like that, what happens is the base and the acid can react. Okay, and because the acid releases H plus, so this hydrogen will be lost as H plus. Okay, so if we lose it, we have H plus. What happens to the COO minus? What charge would it develop? Minus. Okay, so we hold on that thoughts for a while now. And then there's the basic part of this molecule. It has a lone pair and it can gain that H plus. Okay, so say this H plus goes here, right? So this one tadi is negative. Now we have an additional hydrogen on the nitrogen. So what charge would that nitrogen develop? Positive. Okay, so you can see that there's a positive charge on the amine group. Initially NH2, now becomes NH3. And then there is a negative charge on the COOH group. Initially COOH, now COO minus. Okay, so we will write this as a reversible reaction because they can lose and gain these protons all the time. So I keep my hydrogen and R group the same. My carboxylic acid now becomes carboxylate. My amine group now become ammonium. I will make that as, okay. Do you learn this in bio? Internal transfer nada. Okay, that's fine. So you can see that there is a dipolar. So this is called a dipolar ion because it's got negative and positive charge on the same molecule. Now, if you have 1+1 charge and 1-1 charge, overall charge of the molecule is still neutral. Okay, so Zwitterions is still a neutral molecule, but it has the positive charge on one side of the molecule and the negative charge on the other side of the molecule. So this is what happens. And this is an example of a Zwitterion. Where the word Zwe means two. Okay, it's in German. Two, because there are two charges in the same molecule. Okay. Sometimes they will just write this Zwitterion in a structural formula, okay? But here I show you the displayed structure so that you know where the internal proton transfer is happening, okay? Right, properties of amino acids. So same thing, this is the same thing that we were looking at. Amino acids are high melting point crystalline solids. Why do you think they have, well, it's there. Well, the reason for the high melting points is because they are made up of ions, right? So ions, when you have oppositely charged, ions forming a bond with each other, what do we call this bond? What kind of bond would you expect to have between one molecule of zwitterion and the other molecule of zwitterion? Sorry? Ionic bond. Yes, they will form ionic bond. So even though it is an organic molecule, and we say that, well, is an organic molecule a simple molecular structure? Zwitterion will form an ionic bond with its neighboring zwitterions. Okay? So this explains why amino acids are high melting point crystalline solids. The word crystalline there is a characteristic of an ionic bond. The strong electrostatic forces of attraction between dipolar ions account for the high melting point. So you can mention ionic bond between the molecules. Okay, in terms of solubility, amino acids are insoluble in nonpolar solvents but soluble in water. Same thing, because water is a polar molecule, zwitterion is also a polar molecule. Okay, so the interaction that it has with water is called ion dipole interactions. Why do we have these ion dipole interactions? For example, okay, water, if I just draw water as this, okay, and then we know that water has two lone pairs, and because of the oxygen, electronegative oxygen, it develops a delta minus, and the hydrogen will become delta plus. Okay, so imagine this is solubility interaction. So the attraction is between the slightly positive hydrogen and the fully negatively charged COO minus. Okay, so this interaction is called ion, because COO minus is an ion with a full negative charge, and this is called dipole. So that's why you have an ion full charge dipole interaction. Okay, so this is mentioned in your notes but not highlighted. So please highlight that ion dipole interactions with water molecule. And the name comes from this attraction. Okay, so that's not really a hydrogen bond. It's a different interaction, which is called a ion dipole interactions. Okay, so they will not dissolve in organic solvents. Non-polar solvents, they don't mix with the non-polar solvents. Okay, now because amino acids have both the acidic group and the basic group, this means that they can act as both acids or base. And so we call them amphoteric. You still remember this word, amphoteric, from last year AS, when an oxide can act as an acidic oxide or a basic oxide, we call them amphoteric. Same case for zwitterions. Since they have both the acidic and the basic properties, they are said to be amphoteric. Amino acids can also act as a buffer solution. Buffer solution is from topic equilibria, ion equilibria this year. So a buffer solution is a solution that can resist changes in pH when small amounts of acid or small amounts of base is added. Okay, right. We're going to look at how these amino acids can behave as a buffer solution. Okay, what happens to these amino acids when we add small amounts of acid or small amounts of base? Okay, so first we're going to look at increasing the pH of the solution, right? Say your amino acids is dissolved in water, and the solution is usually, if it's in neutral, then it would have, sorry, if the pH is neutral, zwitterions would also have a neutral charge molecule. Okay, you'll see that later. But what happens if we add an alkali? So adding an alkali is the same as increasing the pH. Yeah. So okay, I'll draw the molecule first. We start with Zwitterion. So what happens? I am going to draw my drawing this time. I don't know why I keep changing. Maybe I'll just put my hydrogen on top and my R group at the bottom. And then NH3 plus, that's my amino acid group. And then my COO minus. That's the amine group, and that's the acid group. I am writing them down in the form of zwitterions. Actually, it's the same thing. Whether you write it as zwitterion or you write it as the normal structure without the proton transfer, they are the same thing. Okay, so adding alkali means we are adding OH minus. Okay, so this is a base. Which part of the amino acid will react with the hydroxide ion? Is it the amine or the COO minus? So is it the NH3 or the COO minus? NH3 plus, okay? So I shouldn't call this the amine group because it's no longer an amine, right? Yes, you are right. So the hydroxide ion will pick up a proton from the NH3 plus, not the COO minus, because this now already becomes a conjugate base, okay? So what happens is that we have CHR. Nothing happens to the COO minus. It stays as it is. And then now my nitrogen will only have 2 hydrogen. So if I have lost my H plus, will I have any charge left on the nitrogen? No more, okay? My other product form would be H2O. Do you agree? H2O? OH minus gains a H plus, it becomes H2O. Okay, now this is in an alkaline condition. What can you say about the charge of the amino acid in an alkali condition? Overall charge of the amino acid. Is it neutral still? No, it's now negatively charged. Okay, so we can say that at, never mind, the explanation is already in your notes, so I will just say that this is a negatively charged ion. So at high pH, amino acid exists predominantly as anion and will migrate to the anode when a potential is applied. Okay, so the anion, the reason why the anode is mentioned, potential difference is mentioned because this will be used for a technique called electrophoresis. Have you heard of that process? No? Okay. We'll talk about that later on after we're done with peptide bonds. Okay, so if you read the explanation, the NH3 plus part of the Zwitter ion will donate its H plus ion to the hydroxide, and that NH3 plus ion becomes NH2 after it has donated its H plus. So this causes the Zwitter ion to become a negatively charged ion. So that's at high pH. What if now we add acid, making our solution, the pH of our solution to go down? Okay, so that's exactly the same thing. Okay, so adding an acid to an amino acid. What did I use just now? Green. So same thing, I'm going to put my hydrogen and R group on top. And then I will draw the Zwitter-ion form. Okay. This time plus H plus, which is an acid. So my acid will react with the COO minus. Okay. Because the NH3 plus cannot receive any more H plus. So this H plus will go here to the COO minus to form no changes to the NH3 plus group, no changes to the hydrogen and the R group. The only change that we are seeing is the carboxylate ion now has a hydrogen. So when COO minus receive H plus, the charges cancel out, so that part of the molecule becomes neutral. And no other product form, unless if you have a counter ion. If, say, you have a chloride ion here, that means you will just have a chloride ion lying around in the solution, okay? But here we just show it as H plus. So what is the overall charge of this amino acid? Positive, okay? So it becomes positively charged ion. Okay, so the COO minus part of the Zwitter ion will accept the H plus ion to reform COOH group, neutral. This causes the Zwitter ion to become a positively charged ion. That positively charged ion comes from the nitrogen. Okay. So hence, at low pH, amino acid exists predominantly as cation and will be attracted to the cathode or the negatively charged electrode when there is a potential difference applied. You okay with this? Okay. So to summarize, amino acids can therefore exist in three forms depending on the pH of the solution. Okay, so that's our summary here. Okay, so if the amino acid is in a solution that has a pH 7, then it will exist as a Zwitter ion. And Zwitter ion, even though the name is an ion, it is still neutral. Overall charge is 0 because +1 and -1 cancel out. At low pH or at acidic region, amino acid exists as a positively charged ion. At high pH or at an alkaline condition, amino acid will exist as a negatively charged ion. Okay? Remember the word just now I said isoelectric point? Okay, so just highlight. Isoelectric point means it is the pH at which amino acid exists as a neutral Zwitter ion. So that's the definition of isoelectric point. The charges, iso means same, electric means the charges are they just cancel out lah, the +1 and the -1. Okay. Next, we're going to look at peptide bonds. Those are amino acids. Now we want to look at peptide bonds. And peptide bonds actually is similar to an amide bond, except that peptide bonds is specifically called when you use amino acids. Okay, so for amide bonds, you just use any amine and any carboxylic acid or acyl chlorides. But for peptide bonds, it's specifically coming from the formation of amino acids. So describe the formation of amide in bracket peptide bonds between amino acids to give di and tripeptides. Have you um, learned about the formation of peptide bonds from amino acids? Yes? How about in polymerization? When many amino acids come together and then they form a long chain? No? Okay. Right, so amino acid molecules can react with each other because they have the acidic group and the basic group. Not only that they can have an internal acid transfer, proton transfer, they can also react with one molecule of amino acids with another molecule of amino acids, okay? So when two amino acids react together in a condensation reaction, a dipeptide is formed. So please remember that the formation of a dipeptide or a tripeptide is called a condensation reaction. When we combine the two molecules of amino acids together, in the process, we also lose something. Okay, so usually we lose water, H2O. Okay, so let's see how this is a condensation reaction. So I've got amino acid 1, amino acid 2. During the formation of dipeptide, the only two functional groups that are involved is the amine and the acidic group. The R group and the hydrogen will not be involved. Okay? So I usually put R and H out of the way, all right? Not along the chain. Okay, so during this condensation reaction, the OH from the carboxylic acid and the hydrogen from the amine group will be lost as water. That's why it's called a condensation reaction, formation of water, okay? So as we combine these two amino acids, 1 and 2, we are also losing water, which is not shown in this equation, but I'll just add that on, H2O. Okay, and then you can see that we form the C double bond O NH bond, which is an amide bond really, but since it is made up of amino acids, we call it a peptide bond. And because we have two peptide bonds, no, because we have two amino acids to make up one peptide bond, we call it a dipeptide, okay? So the dipeptide depends on the number of amino acids. The most common mistake made by students is that, oh, a dipeptide, that means I have two peptide bonds. No, there's only one peptide bond made up of two amino acids parts. Do you notice that I can also form the COOH part of amino acid 2 with the NH2 part of amino acid 1? Yeah? There is another combination. Here you see COOH of 1, NH2 of 2, but I can also combine the COOH of 2 with NH2 of 1. Okay, we'll look at that later. The possible combination of the formation of dipeptide. Okay, what about tripeptide? Same thing. I've got 3 amino acids. This is amino acid 1, amino acid 2, and amino acid 3. Do you have this diagram in your notes? Okay, so it's a little bit small. I couldn't find a clearer diagram for this one. Okay, same thing. I will put the NH2 and the COOH on the sides, the hydrogen and the R group top and bottom, because they are not involved in the formation of the peptide bonds, okay? So again, I lose OH from the carboxylic acid part of one molecule, and I lose hydrogen from the amine part of another amino acid molecule to form a C double bond O NH bond. That's my first peptide bond. And then the second molecule of amino acids will also form a peptide bond with the third amino acids. Same thing, I lose water in the formation of the new bond. This is called a tripeptide bond because there are 3 parts of amino acids. 1, 2, and 3. It doesn't depend on the number of peptide bonds. There are only 2 peptide bonds here, but the name tri comes from the number of amino acids involved in making this molecule. Okay? And don't forget, you lose 2 molecules of water to form a tripeptide. Are we all okay with that? Okay. Example 1, 12.1, dipeptide. The 2 simplest amino acids, glycine and alanine, would be shown. Okay, so what makes them different is the R group. You see, one, the R group is hydrogen, the other one, the R group is a methyl group. But we're not interested in the R group, and we're also not interested in the hydrogen. To form a dipeptide, we're only interested in the amine and the acidic group. Okay, so there are 2 ways of doing this. You already have the diagram. Okay. So glycine and alanine can combine together with the elimination of a molecule of water to produce a dipeptide. The reaction is a condensation reaction, as a small molecule is eliminated when reactant molecules join together. It is possible for this to happen in one of 2 different ways, so we might get 2 different dipeptides. Okay, so what do I mean by this? Peptide link formation 1. Let's start with, I will start with glycine and alanine. Okay. I will draw my glycine maybe to the side. Okay. I will change the color so you can see the 2 difference. So glycine, again, I will put the hydrogen and the R group top and bottom, and then NH2, COOH. Okay. Now, if I want to form a peptide bond, this carboxylic acid needs to be next to an amine group. Okay. So alanine, I'll just try to draw them as close as possible so you can see where the connection is being formed later on. CH3, COOH. Okay, so my dipeptide bond will happen at the acidic part and the amine part. Okay, so that's easy. I lose water. CH, O. A new bond form here with nitrogen, and my nitrogen has only 1 hydrogen left. CH, CH3, 3 double bond OH. Okay, so I will just highlight the peptide bond. That's called an amide or peptide link. We call it peptide link, peptide bond, same thing. That's the first possible combination. There is another possible combination. Can you see it? Can you see it? Can you see that this amine can react with this acid? Yeah, because we haven't done that combination yet. So that's our second. I'll just copy this down. Can I? Yeah, I can. Done. So that's one way. peptide link formation 1. The other one is using the other functional group that we haven't used yet. So it's a different, separate reaction. Okay? Are you done with this? Some of you still copying this down, so I will not change it. But if you already can see the second peptide link formation, then you can start drawing them out. Okay, done? Okay, next one, peptide link formation 2. Still the same, but I'll just erase this. It is still the same amino acids, but just different site. It's the other side. So that means I will move the glycine here and the alanine will be there. Okay, so let me just do that. Right, and this time, same thing. It's the hydrogen from the glycine on amine group and the OH from alanine on the COO minus group to form another version. You may think it's the same, but it's not the same. NH COOH. Make sure you already remove the hydrogen on the nitrogen, yeah? And again, this is our amide or peptide bond. Okay, now when reading a chain of amino acid, where do you start from, the N terminal or the C terminal? Is there a specific rules for you for biology? But you do know the N terminal and the C terminal, right? The N terminal is when you start from the amine group to the COOH, yeah? Same thing, in this case, amine group to the COOH. If you try to put these two dipeptides side by side, I think you can see it on your notes. These two are not the same, okay? They are different. Plus H2O, don't forget, because I forgot about that. Plus H2O as the side product, the molecule that is being eliminated, plus H2O. Okay? So you can imagine, if many amino acids are joined together, say, I don't know, more than 3, in a protein structure, you would have thousands, 10,000s, 100,000s of amino acids, because amino acids is the starting, the smallest building block for a protein, right? So when you have a lot of amino acids, forming amide bonds or peptide bonds, we call it a polypeptide. Okay, we will look at, no, we won't be looking at polypeptide, but we will be looking at the polymerization of the formation of amide bonds. So proteins are made up of peptide chains and may contain over 100,000 amino acids. They have a very high molecular mass and are more complex in structure than polypeptides. Proteins could be hydrolyzed into its constituent amino acids by refluxing it with aqueous sodium hydroxide or dilute sulfuric acid. See hydrolysis of amides. So when you break down the peptide chains, it is exactly the same as hydrolysis of amides because you are breaking down the amide bonds. Okay, so the conditions, the products will also be the same. The peptide linkage is broken during the hydrolysis to give back the amino acids. Okay. Right, so that's what's happening. Here is an example of hydrolysis. Okay, so this is just showing you 4 parts of the long polypeptide chain. So you are breaking the C N bond because that's the bond being formed during condensation. All right. So you break that bond, you will get the individual amino acids. So this is called the hydrolysis. It's the same as the hydrolysis of amides. Okay, so that is all for today. Tomorrow, I think we can finish off the topic, just electrophoresis. Maybe we'll do some questions that's very, very short part only. Okay, so yeah, we'll stop here. Now, I don't want to rush through the electrophoresis. Nina, can you please stop the recording? Thank you.